Gauss's theorem. According to Gauss's theorem, net flux through a closed surface, suppose this is a closed surface, net flux to that closed surface phi is equal to Q in by epsilon. Q in, the charge inside that closed surface, and it can be written as is equal to phi, the closer symbol of closed surface, and E dot. This is a complete form of Gauss's theorem. Now let us prove that. Considering a charge Q, electric field due to this charge at a distance R, E is equal to Q by 4 pi epsilon 0 R square. Considering a sphere around this closed surface, this sphere, now we can say that at every point on this sphere, electric field is E and its direction is radially outward. Now we are considering a small area, very small area, del S, on the surface of the sphere. This del S. Now, if del S tends to 0, then we can consider this surface as a plane surface and its direction normal to the surface, and normal, that means we draw a radius, then direction of the del S cap is in this direction. Now from the electric flux, we know that E dot ds, E dot del S is equal to del phi when del S tends to 0. Now, since the magnitude of electric field is constant on every point of the sphere, so we can say that E del S cos theta, in this part, E is constant. And if we sum all this flux, sigma all this flux, del phi, is equal to total flux emitted by the charge Q. Therefore, phi is equal to sigma E del S cos theta, and phi is equal to E into sigma, and we know that del S is normal, so angle between E vector and del S vector is 0 degree because both are parallel. So cos theta is equal to cos 0 is equal to 1. So E into sigma del S is equal to E is equal to Q by 4 pi epsilon 0 into R square, and surface integral of the sphere, surface, if we add all the elementary surface on the sphere, that will give 4 pi R square. So if we cancel this, the phi is equal to Q by epsilon 0. This is, on the other hand, we can express this phi is equal to sigma. From this, we can say that integration E dot ds. So we can say that E dot ds is equal to Q by epsilon 0. On the other hand, if we consider a charge and a surface enclosed by it, it may have any shape. This is a charge Q inside this. Now we consider a very small surface, that is del S. Del S tends to 0. We have to take del S tends to 0 because if it is a very small surface, then we can say that electric field around that surface remain constant. So del phi is equal to E dot ds is equal to E ds cos theta. Now suppose it is at a distance r from the charge r. So at this point, this magnitude of the electric field is Q by 4 pi epsilon 0 R square. Since R is variable on the surface with respect to the point Q, so we can take R as constant. But Q and 4 pi epsilon 0 are constant. Now that is equal to 4 pi epsilon 0 into ds cos theta by r square. Now we know that ds cos theta by r square is a solid angle subtended by the ds cos theta, and ds cos theta by r square is equal to solid angle subtended by the surface S ds at q. Q, that is the point where charge is situated. Now we can write it del phi is equal to q by 4 pi epsilon 0 into del omega. Omega is a solid angle. So phi is equal to, total flux is equal to integration q by 4 pi epsilon 0 solid angle. Q 4 pi epsilon 0 are constants. So q by 4 pi epsilon 0 is sigma, sum of the solid angle. We know that sum of solid angle inside a closed surface is 4 pi. So q by 4 pi epsilon 0 into 4 pi. 4 pi cancel. So this is q by epsilon 0. Thus we can prove the Gauss's theorem. Now Gauss's theorem is very important part because we can calculate the field at a point in some continuous charge distribution as follows. First, a spherical surface. Suppose this is a solid metallic sphere having a charge q. Now we have to find electric field intensity at a distance r from the surface. Now we have to enclose that charges with some surface which is electrically symmetrical. That is, at all points of the surface, electric field is constant. So it is better to choose a sphere around the charged sphere and which is concentric. Now total charge inside the spherical surface, Gaussian surface, is q. Therefore flux is equal to phi is equal to q by epsilon 0 and is equal to integration E dot ds, close integration over the surface S. This is a surface S. And E is constant and is normal to the surface. So we can say that E dot ds is equal to EDS and E is equal to constant, and that is equal to constant and S ds. Therefore, phi is equal to E into surface integral of this sphere is equal to 4 pi r square, and this is q by epsilon 0. So we can say that E is equal to q by 4 pi epsilon 0 r square. Therefore, if we consider all the charge of the sphere centered at the center of the sphere, then we can correctly calculate the field at any point outside the sphere. But if it is hollow sphere, now considering this is a hollow sphere, and we are considering a point inside the sphere, we have to find the electric field on point P, which is inside the hollow sphere. Now, if we construct a concentric sphere around this point, then Q inside is equal to 0. Therefore, we can say that phi is equal to 0, and phi is equal to 0, that means E dot ds, close integral, is equal to 0. So E close integral ds is equal to 0. ds has a definite value, 4 pi r square is equal to 0. Therefore, E is equal to 0. So we can say that at any point inside a hollow sphere, net field is 0. Now we have to find electric field around a long charged wire having linear charge density. Is equal to lambda Coulomb per meter, and we have to find the electric field at a distance r from the wire. Now it is a infinitely long charged sphere, and if we consider any point outside this wire, then the field due to this point, suppose this is a perpendicular, a point just at a perpendicular foot of the perpendicular. So field line will be along this direction. But if we consider another point, the pair of points which is equidistant from this foot of the perpendicular, so this and this both are equidistant from. So resultant field due to this 2-point charge will be along these two directions. And if we resolute it, we will observe that the resultant field will be along the perpendicular bisector of this. So we can say that all the field lines at every point outside this sphere is radially outward. That is, if we draw a perpendicular, then field lines will be along this direction. And if we consider a surface which is radially at a constant distance, that will be a cylinder. So we can consider a cylinder around this point as a Gaussian surface. Now, considering a cylinder, same radius, the cylinder, and the surfaces of the cylinders are a circular surface at the top. Suppose this is S1, another surface, circular surface at the bottom, this is S2, and a surface, curved surface, this is S3. If this is R and the height of the cylinder may be H. So total charge inside the cylinder, Q in, is equal to H into lambda Coulomb. Therefore, flux phi is equal to Q in by epsilon 0 is equal to H into lambda divided by epsilon is equal to E dot ds. Therefore, H lambda by epsilon 0 is equal to E dot ds over the surface 1, E dot ds over the surface 2, and E dot ds over the surface 3. Now, the direction of the surface S1 along normal to the surface, that is in this direction, and we know that at every point direction of the field along this direction. So direction S1 cap is along this direction and R1 cap along this direction. Both are perpendicular to each other. So we can say that E dot ds for S1 is equal to 0, and same as direction of S2 along this direction, and this is S2 cap, and this is direction of E along this direction, and they are 90 degrees to each other. Therefore, this also 0. Only the surface, curved surface, as field is radially outward, we have explained that at every point direction of the field normal to the surface. So we can say that direction of the surface and the direction of the field at every point of the surface is parallel. So this will be S3 E into ds. So E, curved surface area of the cylinder, is equal to 2 pi r into h. H into lambda divided by epsilon 0 is equal to. So h is cancelled. So E is equal to lambda by 2 pi epsilon 0 into r. Now, if you consider a cylinder, charged cylinder, long charged cylinder, the long charged cylinder, and surface charge density of the cylinder, surface charge density cylinder sigma Coulomb per meter square. Again, for the same reason, electric field due to this cylindrical charged surface is radially outward. Suppose radius of this cylinder be r, capital R, is the axis of the cylinder, and we have to find the field point outside the cylinder at a distance. Again, we will enclose this point by a Gaussian surface, and that will be the cylinder. Now, first we have to find the charge enclosed in this Gaussian surface. Q in is equal to surface area enclosed inside the Gaussian surface is equal to 2 pi r into h, h be the height, into sigma. Sigma is the surface charge density. So this is the QE. Curved surface area into surface charge density. Therefore, phi is equal to Q in by epsilon 0 is equal to 2 pi r h sigma divided by epsilon is equal to enclosed surface E dot ds. We can divide all the surface into three parts. One, the top part, suppose this is S1, bottom part, this is S2, and the curved surface S3. So 2 pi r h sigma by epsilon 0 is equal to E dot ds over S1 plus E dot ds over S2 and plus E dot ds over S3. Since the direction of the field, radius, that is radially outward, as it is taken positive q, therefore E dot ds of surface 1 is 0 because direction of the surface is perpendicular with the direction of the field, and this also 0 because direction of the surface is perpendicular to the field, but this is 90 degree. Field is perpendicular with the surface, that is direction of the field and direction of the surface is parallel, that is makes a 0 degree angle. So this is ds of surface 3 is equal to E into 2 pi r to h, 2 pi r h into sigma divided by epsilon. 2 pi h cancelled, so E is equal to r sigma divided by epsilon 0 into r. Now from this we can get that if r is equal to r, that is at the surface of the cylinder, charged cylinder, when r is equal to r, then E is equal to sigma by epsilon. So at every point of the charged cylinder, uniformly distributed charge cylinder, E is equal to sigma, that is surface charge density, divided by epsilon 0. And it is true for all surfaces. Now, in case of a very long charge sheet, suppose the charge sheet very long, we are taking very long charge sheet because the field lines are normal to this charge sheet, that is perpendicular to the charge sheet, charged. Since it is a very thin charge sheet, and suppose surface charge density sigma, surface charge density is equal to sigma, and this is thin. So if we consider a small area over this sheet del S, the flux of this thin sheet will be in both directions, that is in downward and upward direction. We have to find the electric field at a height r from the surface. So this is, we are taking r from the top and also r from the bottom. Therefore, this cylindrical part, the lines of force or field lines crosses on this surface normally, and the direction of this surface and the field lines is perpendicular to each other. This is 90 degree and this is 0 degree. Okay? So Q in is equal to sigma into del S. So flux phi is equal to sigma into del S divided by epsilon. So sigma into del S by epsilon 0 is equal to E dot ds, and there are three surfaces, one S1, one S2 and third S3 is equal to S1 E dot ds plus S2 E dot ds plus S3 E dot ds is equal to angle between area vector and field vector for S1 is 0 degree, so it will be E to plus, and it is also E into equation ds, and this is 0 because S3 is perpendicular, is equal to E into 2 into del S. Therefore, E is equal to sigma by epsilon 0. So it is clear that in case of long sheet, charge long sheet, field at a point over the sheet or under the sheet is same, and it is independent of the distance of the sheet. Now if it is a 2 epsilon. Now in case of thick sheet, thick plate, that is, we consider the thickness of the plate. In case of thin sheet, we know that in metallic sheet there is no charge inside the metal, all charges come out at the surface, and sigma be the surface charge density. Now the charge at this top surface will emit field lines in upward direction, and charge at the bottom will emit the field lines in downward direction. Therefore, if we consider a portion del S, and we have to find the field at a point r distance from the surface, this is r, this is also del S. Therefore, Q in is equal to sigma into del S, and we are taking the surface del S just below the top surface of the sheet. Therefore, we can say that there is no field at this S1, and this is say S2, and this is S3. So Q in by epsilon 0 is equal to sigma into del S divided by epsilon 0 is equal to close integral E dot ds. Process. Now sigma into del S divided by epsilon 0 is equal to S1 EDS plus S2 EDS plus S3. Therefore, now S1, as it just below the surface and there is no field line inside the metal sheet, so this is 0, and angle between field vector and S vector for S2 surface is 0 degree, so it will be E integration ds of S2 plus, and angle between field vector and the area vector is 90 degree, so this is 0. So is equal to E into del S. Surface integral of the surface is equal to del S, sigma del S by epsilon. Therefore, E is equal to sigma by epsilon 0. So it is just twice of the previous. For thick it is sigma by epsilon 0, and for thin it is sigma by 2 epsilon 0. Reason is, in case of thin, a charge emits field lines in two directions simultaneously, but in case of thick, only it can emit the field lines over the surface. Now we will discuss some popular problems. Suppose this is a square of side A, and a charge is kept at a distance a by 2 from the center of the square, and the charge is Q. Now we have to find the flux crossing this surface. If we consider a Gaussian surface, then that will be a cube of side cube, and the charge is at center of the cube. So we can say that the flux emitted by this cube will be equally distributed over the 6 surfaces of the cube. Therefore, total flux phi is equal to Q by epsilon 0, and flux through each surface will be 1/6 of the whole. That is 6 pi. That is the answer.